All right, welcome everybody. It's dynamics and number theory in New England. Now we are joined from Midwest, Tushar from University of Wisconsin, talking about using templates to study problems in dynamics and number theory. Welcome, Tushar.
Thanks, Dima, for the opportunity to speak at one of my favorite seminars. I just want to start by thanking the organizers, Dima, Keith, Philippe, and Han, for all their efforts to put this together, because since last year things have been pretty tough, and this has been a great way to lift our spirits during these challenging times. So before I start, I've just put in the chat a copy of the slides. So if you want to download the slides, they are in the chat. If you can't download them for some reason, then you can just email me and I'm happy to send you a copy of the slides. Okay.
Thank you.
Great, so let's get started. So I'm going to talk about an idea called templates and how one might use them to study problems in dynamics and number theory. So it's joint work with my brilliant collaborators. So I thought I'd start with a little humor. This is a quote, maybe some of you recognize it. I have said that Texas is a state of mind, but I think it's more than that. It's a mystique, closely approximating a religion. And this is true to the extent that people either passionately love Texas or passionately hate it. And as in other religions, few people dare to inspect it for fear of losing their bearings in mystery or paradox. So I don't know whether any of you have read Travels with Charlie, but this is by Steinbeck. And all my collaborators are from Texas. They're all based in Texas right now. One of them was actually born and brought up in Texas. Well, no, not born in Texas, but brought up for most of his youth in Texas. That's David. And David and I got our PhDs with Mariusz in 2012 at UNT in Texas. And Lior joined, I think, a year before we graduated in 2011. And he brought a bunch of ideas, including Schmidt games, to North Texas. And David, Mariusz, and I were working on a lot of problems involving dynamical systems, things like Julia sets, Kleinian group limit sets, etc. And in that 1 year, we just really, there was an explosion of ideas. And even if it's 2021, basically, I feel like I'm still in grad school trying to finish the projects that we started. They never seem to stop. But that's a bit about the three of us, the four of us. Okay, so every talk in Diophantine approximation secretly should start with Dirichlet's theorem. So let's start with Dirichlet's theorem. So for every real m by n matrix A and every parameter Q, there exists an integer PQ such that AQ minus P, the error, is bounded above by this height for all for the magnitude of Q to be bounded between 0 and that parameter that you chose. Okay, so of course, this was first known for real numbers using continued fractions by Legendre before Dirichlet. Dirichlet discovered his box of drawers principle that was popularized by Erdős and Robinson as the pigeonhole principle to prove this. And linked to what I'm going to talk about today is, later, probably about 40 years later, Minkowski gave a nice proof of this using his geometry of numbers. And so, yeah, this is sort of like a discrete versus a continuous version of this pigeonhole principle. Some of you may know about such approximations with various names. In some papers, this is called Diophantine approximation for systems of linear forms, because you can basically think of this matrix A as having, M linear forms in n variables. Okay, and so this was intensely studied amongst number theorists like Minkowski, Khinchin, Yarnik, Cassels, Davenport, Baker, Schmidt, and Schmidt. And then I stop at Schmidt for a second before mentioning the next list of names, because at this point, there was some sort of a paradigm shift, because people realized, especially Schmidt, Margulis, and Dani, they started realizing that there was this interaction or this interface between looking at problems about Diophantine approximation per se and looking at dynamics of certain flows on homogeneous spaces. And then this was followed by Margulis, Dani, Shah, Weiss, Kleinbock, Brouillard, de Saxe, Yang, and this list goes on. And I know some people at talks like to say that it's better not to name anyone because people who aren't named will get irritated, but I don't subscribe to this. I think that's just being lazy and you're not reading your literature. So it's better to name a list and then ask the audience for forgiveness and for input for which names have I forgotten. So feel free to email me and give me comments and feedback. Okay, so the names I mentioned, Schmidt, Margulis, and Dani, let me tell you a bit about them from the 80s. So this is this interface I was talking about. So in Lumini in 82, Schmidt was giving a lecture at this conference, which included really the top people in sort of transcendental number theory at the time. So that's the name of the conference. And here's the viewpoint. It says that the classical theorems in the geometry of number deal with one convex set and one lattice at a time. So that's Minkowski. While in Diophantine approximation, instead of dealing with one convex set and one lattice at a time, one deals with a parametrized family of lattices, or you could think of it as of convex bodies. And then he goes on and he talks about, okay, maybe we should start studying Minkowski's successive minima. I will define that later in the talk. And then he finishes his report. I wanted to end this by saying that our list of questions could be easily expanded. But even favorites of the author, such as metrical theorems and uniform distribution, have been left out. So we will talk about some metric Diophantine approximation today. So the next sort of quote I wanted to mention was by Margulis. And this was in Washington, DC for the 2009 AMS colloquium lectures, where Margulis was again reminiscing. During the last 3 decades, okay, so past 2009, so we're back in the same period as Schmidt was talking in the 80s, it's been realized that some problems in number theory, and in particular Diophantine approximation, can be solved using methods from the theory of homogeneous flows. And then a few pages down, this was actually 3 lectures. The notes are available at this link. They're beautiful. I strongly encourage you to download them. And then a few paragraphs down, he talks about this amazing work with Dima, where they prove the Baker-Springschup conjecture. And I want to point out that the proof of theorem 17, which is stated here, is based on Kleinbock Margulis. is based on a method which uses the correspondence originally introduced by Dani in the mid-1980s between approximation properties of vectors and the behavior of certain orbits in the space of unimodular lattices in Rn. So what is this correspondence? This is Dani talking about it or reminiscing about it at Margulis's nth birthday conference. So in the mid-80s, I observed that the notion of singular systems of linear forms and badly approximable systems studied by Schmidt correspond to trajectories of points on the space of unimodular lattices in Rn. Under the action of certain diagonal one-parameter subgroups, which I'll remind you about, being divergent or being bounded. So this was a beautiful paper from 1985, where Dani states what Margulis refers to as the correspondence principle. So here's the Dani correspondence principle. So if you fix M and N and you let D equal their sum, let's look at SLDR mod SLDZ. And for every T, or every real number T, let's consider the matrix GT. So this is a diagonal matrix. And for every M by N matrix A, let's consider this matrix UA. Okay, so a little bit of matrix multiplication will tell you that this happens. And so here's the error of approximation. There's the height. And so what this tells you is that Diophantine properties of A can be translated into dynamical properties of this flow, or semi-flow, if you like. So for example, as Dani was mentioning on the previous slide, a matrix is singular if and only if this flow is divergent. It's badly approximable if and only if this flow is bounded. And of course, those are the two we mentioned, but this story goes on and was developed by several authors, including Kleinbock and Margulis. And so I just gave a sample other class that some of you will be familiar with, the very well approximable matrices. Okay, so this gives you a way to study Diophantine classes by studying homogeneous flows. Okay, so apart from having this beautiful dictionary, let me show you one way this dictionary or this correspondence is a unifying principle. So for example, when these classes were first studied in Diophantine approximation, long before the 1980s, at least more than half a century before the 1980s, several people worked on cases of showing that these sets of badly approximable or singular or very well approximable matrices are Lebesgue null sets. If you follow the Dani correspondence principle, you sort of get all of this in one stroke just because the GT flow is ergodic. So this is a unifying principle because it shows you how to look at all these individual proofs in one framework, right? So the ergodicity of this GT action implies that it suffices to show that, to show that all these are Lebesgue null sets, that any trajectory that equidistributes is not in these respective sets. And of course, an equidistributed trajectory can't be bounded because, its orbit must be dense if it's equidistributed. It's not divergent, it doesn't escape to infinity at a linear rate, etc. So beyond showing that these sets are null sets, the next question, the next natural question is, okay, but these sets are large. How do we quantify their size? And so a huge line of mathematicians, again, this is a very incomplete list, but I think that line starts with Jarnik, who was writing soon after Hausdorff's introduction of his dimension in 1919, immediately picked up on this, and Jarnik and Besekovich were among the pioneers who started studying, okay, how do we capture or how do we try and compute the Hausdorff dimension of these sets? So I just thought I'd throw in a small piece of trivia. I think the majority of you would know Felix Hausdorff, but I wonder how many of you have read anything by Paul Mongret. I remember as an undergraduate at St. Andrews.
Same person, right?
Same person, that's right. And if you go to my slides, there's a link, if you click on Paul Mongret, to a beautiful article by a German historian of mathematics on the double life of Felix Hausdorff as Paul Mongret. And I was a student at St. Andrews, and I remember reading this article in the library, and it just blew me away. And after that, I started finding more work. And Hausdorff's complete works are still in process, 9 volumes. So eventually we will have all of Paul Mongret's works neatly published in one place. So I'm not going to define Hausdorff dimension, but instead, I'm going to show you how you should think about Hausdorff dimension. So this is a combination theorem that combines work of Rogers, Taylor, Tricot, and Cutler. We call it the Rogers, Taylor, Tricot, Cutler density theorem, or theorems. And it's a way to show you how to compute Hausdorff dimension, which you know, and maybe some of you are not familiar with this dual notion of packing dimension. So for those of you who remember the definition of Hausdorff dimension, you're using coverings. And for packing dimensions, you use packings rather than coverings. So it's dual in that sense. But I hope to impress upon you that this duality is actually much more than just what I said. So let me introduce the lower and upper pointwise dimensions of a measure, mu. Okay, and so mu is if you're wondering, it's a locally finite Borel measure, let's say on RD. So the lower and upper pointwise dimensions are, oh, sorry. Please, go ahead. Go ahead. Okay. Yeah, just let me know if there are any questions at any point. Right. So the lower and upper pointwise dimensions of a measure mu at the point x are defined as written. Okay, so this is the lim inf of this scaling, and this is the lim sup of this scaling. Right. So you're measuring sort of the rate of growth of a ball with respect to its radius as the radius is going to 0, right, as you're zooming in on the point. So given such a measure mu, then for any Borel set A, it turns out that if you can bound this lower pointwise dimension, you're really bounding the Hausdorff dimension. And if instead you can bound the upper pointwise dimension, then what you're doing is you're really bounding the packing dimension. And this is how you should really think of Hausdorff and packing dimensions. You should forget the definition, and you should just remember this theorem. So this is what I was just saying. So if you've got a bound, let's say you can bound this lower pointwise dimension above by S, then that means you've got an upper bound again for the Hausdorff dimension. And if you've got a lower bound on the lower pointwise, then you've got a lower bound on the Hausdorff dimension. And as you can imagine, the same principle works if you replace these lowers with uppers, and then the Hausdorff dimension gets replaced with the packing dimension. Okay, so this is really nice. And as I was saying, I was a student at St. Andrews, so I learned this theorem in my second year when I took a class from Kenneth Faulkner, his fractal geometry class. And so this is a link to his books. If you haven't read one of Faulkner's books, you should try. They're beautiful. Okay, so coming back to our question, so what are the Hausdorff dimensions of these sets, right? So B, badly approximable, very well approximable, singular, they're all Lebesgue null. So the next question is, okay, how large are they in terms of, say, their Hausdorff dimension? So it was a theorem due to Jarnik in the seminal paper that I mentioned in 1928. And Jarnik used the theory of continued fractions to prove that the Hausdorff dimension of the set of badly approximable real numbers, or 1-by-1 matrices, is 1. So it's full dimension in the real and the reals, okay? And then I want you to notice there's a pretty big gap, and there's lots of papers in between, but it took quite a while before Wolfgang Schmidt in 1969 could close the case of showing that the same result is true for the case of matrices. And to prove this, he developed what's known famously as Schmidt's game that I mentioned with the slide with Lior a little while ago. Okay, so what about the VWA matrices? So the VWAs also turn out to be a full dimension. And this was, again, initially done by Jarnik and Besikovich independently around the same time. And and then again, you'll notice there was a gap, lots of papers, which I haven't mentioned, before Bovey and Dodson. Unfortunately, I reached out to the York School of Diophantine Approximation for a photograph of Bovey. So I hope to have a photo of Bovey at some point, but I don't have one as yet. So this is Dodson. I'm sorry. So I'm missing a photo of Bovey. If anyone has a picture of Bovey, please send it to me. So it took a while before they could again clarify the situation in the matrix case. It takes a while, okay? So that, remember this, this theme that it takes a while to go from 1D to the general case. And you really need, you need to develop quite a bit. All right, so, and of course, I didn't mention this, but as I was saying in the dictionary, instead of looking at very well approximable numbers, you can define what are called omega approximable numbers or matrices, and then the very well approximable ones are the union of all these omega approximable ones. Okay, so these VWA, in case you're wondering what is this thing, it's like the union for all omega greater than n over m of these omega approximable matrices. Okay, so you can, take a limit as omega goes to n over m, and then this disappears, and you get mn. This formula also tells you, I know some of you are used to thinking about Liouville points. And so, yeah, the Liouville matrices, instead of taking the union, you could take the intersection. And so then you could get the Hausdorff dimension of the Liouville matrices as well. You just take the limit now as omega goes to infinity rather than n over m, right? So instead of letting it go to its least, you let it go to its most. All right, so that was, I guess, what were we? We were back in the 80s with Bovey-Dodson. And then I want you to notice that, okay, we're now in 2007. And in 2007, it took quite a lot of effort. And this breakthrough paper, this is a beautiful paper. If you've not downloaded it, please get it. It's a beautiful paper by Itwa Chung, where proves that the Hausdorff dimension of the 2-1 singular matrices, okay, so these are like singular vectors, is equal to 4/3. And I want you to notice that if you look at this paper and you look at the bibliography, you'll notice that there's scant information about this set. There's maybe a few papers, but this was quite challenging. And of course, this was a problem that was known to everyone, including Jarnik, Kinchin, Besikovich, all of them for a long time. So this was a real breakthrough. And I want to just point out that it was 2007, and I want you to remember we're doing 2 by 1. Okay, so like the smallest situation where singular matrices make sense. I forgot to mention, let me just say, in case you're wondering, why aren't we doing 1 by 1? Well, if you look at Singh, this is just a small remark in case you're wondering. The 1 by 1 case is boring in terms of dimension, because Singh 1-1, so the singular numbers are just the rational numbers. Okay. So the first non-trivial case is Singh 2-1, and then by using a certain duality principle due to Jarnik, you can get Singh 1-2 as well. Okay, so then in 2014, ITWA was joined by Nicolas Chevalier, who gave a beautiful lecture at this seminar a week ago. And they proved that, okay, instead of looking at 2-1, they could do it for M1. Okay, so for vectors in general, not just for the smallest non-trivial vectors. And so the 4/3 comes out as a special case of this next result that came about 7 years later. All right. So what about the matrix case? So that's when this beautiful paper came out, which we'll refer to as KKLM. Before I tell you the result, what I find very beautiful about this paper is that this is a paper involving a grandson, a son, and a grandfather. So I recently was involved in a joint project where I could write a paper with my academic father, my grandfather, and my aunt. And I'm sort of on the lookout for such papers. If you see such papers, let me know. This is quite rare, actually. Okay, so what did KKLM do? They proved that in the general case for matrices, okay, not just long, skinny matrices or short, flat, long ones. So instead of vectors or forms, if you just look at an arbitrary matrix, they could prove that this Hausdorff dimension was bounded above by this quantity. Okay. And I just want to mention a bit about the ingredients that go into such things. So using continued fractions, Jarnik could bound the set of real numbers whose Hausdorff dimension is less than equal, the Hausdorff dimension of the set of real numbers whose continued fraction partial quotients, right? So the digits of the continued fraction of these numbers were bounded above by, say, n. And the badly approximable numbers are the union of such sets. And so you can get, after you can prove such bounds, that in the limit, you get full dimension. And Schmidt developed his topological game, as I said, to extend Jarnik's result to the matrix framework. And Dodson and Bovey developed this system of regular and ubiquitous systems. And this also, in part, was inspired by the 1D proofs of Jarnik and Besikovich, but things get a little trickier in higher dimensions. Okay, so what about Chung and Chung Chevalier's results? They also had to develop new techniques. unsurprisingly, if the previous people knew how to do singular, you can bet that we wouldn't have to wait till 2007 for that result. I want to point out one important word here, equality. For those of you who have played with Hausdorff dimension, you'll know it's pretty challenging to get your hands on the Hausdorff dimension of sets. And there's often an interplay between upper bounds and lower bounds. And the lower bounds often involve creating measures supported on the set. And that's sort of what I've referred to here. And it's trickier in general. So though KKLM could work with matrices rather than vectors, they couldn't get equality, and they used the highly non-trivial sort of breakthrough work by Eskin, Margulis, and Moses, where they were working on the quantitative Oppenheim conjecture. So they leveraged this technology of integral inequalities to get their upper bound. I also want to point out, in case you're wondering, the methods of these two papers are orthogonal. So there's no overlap as far as I can see. But again, I am in a group here of absolute experts who know much more about all this than I do. So I'm looking forward to your criticism and feedback. Okay, so here they are. This is KKLM, and this is CC. And this is a picture of Jan Bourgeot, who joined CC. And here are two questions among several questions that were posed by these authors. So here's one of the conjectures from KKLM's paper. They proved the upper bound, and they actually conjectured that their upper bound was sharp, but they had no way of showing that it was equal. Certainly, if they did, I think all of us in this room respect these authors quite immensely. It would not be left as a question. And I also want to point out a particular question from BCC. So BCC took the question all the way back to it was first result. You might remember that this Hausdorff dimension was 4/3. And the Hausdorff dimension, if you remember the lim inf and the lim sup aspect of my slide on Hausdorff and packing dimensions, you'll see it's obvious that the Hausdorff dimension is less than or equal to the packing dimension. And so they asked, even in the case of Sing to 1, what happens? Is this equal or is this strict? Okay, and so here's a sample application of our result. And so this is a corollary of what we call our variational principle, where we could, for example, answer these two questions. And so we could show that the Hausdorff and packing dimensions are always equal to this number. Then I'm going to just now, from now on, I'm going to just call it delta mn. Okay, so delta mn you just remember it's the Hausdorff dimension of the singular, or the packing, if you like. Now, one cool thing about our paper, So one thing about our paper is that we had to make a decision on how to present it, right? So did we present a bunch of theorems about metric Diophantine approximation, or do we present a number of theorems about homogeneous flows? And so we took the decision not to translate each of our results into the setting of homogeneous flows, but rest assured that you can use Dani's correspondence principle to do that. And I strongly encourage younger members of the audience to do that, because that will lead you to make new conjectures and new theorems in the setting of homogeneous flows. Okay, so for example, in this case, I've done the translation here, but often this will be absent. Okay, let me give you a couple more examples of results. So singularity on average, I heard a beautiful talk by Lifan Guan at the York seminar on Diophantine approximation last week. It's talking about singularity on average. And so given a matrix A, you can define the proportion of time spent near infinity to be this quantity. And let's define a matrix to be singular on average if this proportion is 1. So on average, you are divergent. Remember, singular with the divergent trajectory is the ones that escape every compact set. So again, KKLM proved that the Hausdorff dimension of the set of singular on average matrices is at most delta Mn, and also conjectured that this should be sharp. And we could prove that. And we actually have a formula that tells you that if you choose the proportion of time you want to spend near infinity, then your Hausdorff and packing dimension is given by this formula. Okay. So when P is equal to 1, you just get delta Mn. In Chung's paper, Chung resolved a beautiful question, which was, I don't know whether it was conjectured, but I certainly know it was a question in Starkov's book. Are there singular vectors that are not VWA? Okay, so if you're now trying to specify, you're saying, okay, I want to go off to infinity. I want to diverge to infinity, but I want to do so at a pretty slow as possible, right? Like, can I slowly diverge off into the cusps? And so let me just define A as psi approximable. This is, of course, to several members in this audience, you know much more about psi approximability than I do. So a matrix is psi approximable if there are infinitely many integer pairs such that this happens. And I just want to point out that if your psi satisfies an inequality like this, so if there's some constant c greater than 0 such that psi of q is greater than c times q to the n over m, then every singular matrix is psi approximable. So for any psi where this doesn't happen, Chung actually showed that there's a singular vector that's not psi approximable. And Chung did more than this. He actually showed that there's a dense set of such vectors. And so our main theorem can quantify Chung's theorem and generalize it to the matrix setting. So now we can say that, yeah, that dense set of answers to Starkov's question has full Hausdorff and packing dimension. And when I say full, I don't mean equal to Mn, I mean equal to delta Mn. So full in the set of singular matrices. Okay, and so then this is just the translation for those of you interested for the same result, but using Dani's correspondence principle. Okay, so all of the results stated so far are consequences of this single theorem that I was calling the variational principle. And again, I just want to point out that this variational principle gives a unifying perspective, right? Because now all those results, like even the results for the Hausdorff dimension of BA, VWA, and singular fall under one framework. It's just one theorem. You don't need separate methods. You don't need separate techniques to prove them. And there's no dependence on the methods of KKLM, Chung, Chevalier, Bugeaud, Chung, Chevalier, etc. And I also want to point out, especially for younger members of the audience who are looking for problems, that these theorems are just the tip of the iceberg. Okay, so we spend most of our efforts trying to just prove this variational principle. We put together some applications, but it's really very, very open. Because there are few groups who have started using the variational principle, and they're already doing amazing things, but there's tons of problems. And I really want you to think of creating new problems. And if you create some new problems and perhaps solve some of them, please let me know. I would be very grateful for that. Okay, so what are our ingredients as opposed to the previous ingredients that I mentioned briefly? So our ingredients involve two things. Well, one is Schmidt's game is excellent if you want to show that the Hausdorff dimension of your set is full, equal to the ambient dimension. It's not so great for calculating Hausdorff dimensions of things like the singular matrices, which are less than full, strictly less than full, right? And so we created a variant of Schmidt's game that precisely computes the Hausdorff and packing dimension of any set. So it's just a new method or a new way to organize how you think about computing Hausdorff and packing dimensions using a topological game. And the next piece was we extended what's called the parametric geometry of numbers, which was actually first hinted at in that paper I showed you from Lumini in 1982. So this is a lovely paper to look at. All right, so let me tell you a bit about the game, and then I'll tell you a bit about the parametric geometry of numbers. So games people play. This is a photograph of Doa El-Gobashi and Kira Walkenhorst in Rio. So for our game, we'll have two players, Aisha and Bao. And for any beta between 0 and 1, Aisha and Bao will play what we call the delta dimensional Hausdorff beta game. Okay, I'll tell you what delta is soon. And I'm going to define two games. One's the Hausdorff, one's the packing. Okay, so often I'll write Hausdorff respective packing. Sometimes I think I've even written HT/PD. Just okay. So Aisha starts by choosing a starting radius. We're going to play balls, and they're going to have nested balls, as is usually done in these games. So Aisha begins by choosing a starting radius, and then on the kth turn, so Bao responds to each of Aisha's choices. And then once Bao responds, on the kth turn, Aisha chooses a set of sub-balls inside Bao's ball. And then at the next step, of course, Bao picks one of them, and then the game continues. There's some conditions just to make sure that the balls are nested so that one can take the intersection and get what's called the outcome of the game. So here's a picture which probably is much better than the previous slide. So, so let's say Aisha picks this ball. Bao picks this ball. And then Aisha now says, okay, I'm going to give you a set of 3 new sub balls in your ball. And then Bao picks a new one. Aisha now says, okay, I'm going to pick these 4 inside your ball. And then Bao picks this one, and the game goes on. Okay, and so after infinitely many terms, you compute the intersection of these, of Bao's balls, and you get the outcome of the game. Okay, so let A equal to the sequence of these centers that Aisha picked. Okay, so the number that we're writing down here is the number of centers Aisha picked and say like the kth term, okay? And then you calculate these numbers. You'll notice one is a lim-inf, one is a lim-sup. Why? Because these are going to compute Aisha's score. The lim-inf one will be for the Hausdorff game, and the lim-sup one will be for the packing game. And you're going to call a set S delta dimensionally Hausdorff beta winning if Aisha has a strategy to simultaneously ensure that the outcome is in your set and that her score in the game is at least delta. And if you can guarantee that S is beta winning for all sufficiently small beta, then you just say it's delta dimensionally Hausdorff or packing winning. Okay. So the theorem now is that the Hausdorff or packing dimension of any Borel set is the supremum of delta such that S is delta dimensionally winning with respect to either the Hausdorff or packing game. Just for the experts, this theorem works in any doubling metric space. Okay, so any space that's Euclidean in that sense. If some of you know the Bezikovich condition rather than the doubling condition, basically if your metric space is Euclidean, then you can do this. Okay, so that was the game. Now let me tell you a bit about the parametric geometry of numbers. So this was Minkowski. Remember, Schmidt said the geometry of numbers classically was about one convex body or one lattice at a time, but Diophantine approximation should really be about parametrized sequences of lattices or sequences or flows of lattices.
Tushar, could I ask one question?
Yeah, please.
So about the score, the way the score was calculated. So these number of AIs, isn't it always 3? Because Aisha always picks 3 centers. Number of AIs.
So let me, sorry.
Oh, log 3, yeah.
Let me just get the, so are you asking about these two things?
Yes.
Yeah, so, oh, sorry. So I'm really, I must have been unclear about that. So what Aisha is doing, very sharp eye, Osama, is not choosing 3 balls. I skipped over this. I'm really sorry.
I see.
Not choosing 3 balls inside inside Bao's ball, but what Aisha is choosing is a 3 Roque separated set.
I see.
Where I haven't really said what the Roques are, but let's just say that the Roques are involved in getting this nesting condition. Okay, just to make sure that the balls nest so we can get an outcome. And so you're really picking a 3. So this is Aisha's, so Aisha's AK, let's say, in this picture is 3. There's 3 centers. But the next one is 4.
I see. Okay, thanks.
We don't know from this picture, right? Like what it was in the previous. I'm really so. Thank you for asking that. Okay. So games people play. Then we have Minkowski, and now we have our version of the parametric geometry of numbers. So recall from the correspondence principle that if you take any point in G mod gamma, any point x, then this x should correspond to a lattice, right? G of ZD and RD. So there's the formula relating these two ideas. And I want to just remind you, maybe some of you are familiar with it. What's the jth successive minimum of a lattice with respect to a convex centrally symmetric region? For the rest of this talk, you should think of this convex centrally symmetric region as the unit ball. Okay, but the definition is more general. Unit ball with respect to, you know, a norm. And so the idea is that, okay, so you've got your lattice. And then what you do is you start looking at growing your ball. Okay, so R is your ball, and then you just keep making it bigger and bigger. But you scale it by a factor of lambda, and each time you pick up a new linearly independent vector, you remember that time and you call it lambda j. Okay, so the jth successive minimum is the least lambda such that your lattice intersected with the lambda scaled copy of your unit ball contains at least j linearly independent vectors. And so from our perspective, what we want to do is we want to look at the successive minima of the lattices coming from Dani's correspondence principle, right? So as we flow GT mu A of ZD with respect to this unit ball, we want to keep track of these successive minima. Okay, so now the next slide is going to collect all these successive minima. Okay, there's one for every j up to d, and we're going to create a function. So this is going to be called the successive minima function. And in case you're wondering, I've stopped writing with respect to the unit ball. Okay, so this is like, it's there, but it's in invisible ink. We've just thrown it out. But it's there in case you're wondering, what is this convex body? So this is the heart of the parametric geometry of numbers, is for a matrix A. Once you realize what this functional is, then using this correspondence principle, you can now take all of those things about, you know, GT mu A being bounded, being divergent, you know, etc., and transform them into conditions on the first coordinate of this successive minima function. Okay, now, before I continue, I just want to point out something again for the younger members of the audience. Here, I just want to point out that there is at least, I would say, 10 PhD theses waiting to be written. Do you see what's happening here? This is just H1. There is plenty more past H1. So you could create completely new areas of either Diophantine approximation or flows, the dynamics of homogeneous flows, if you start studying this function. So your biggest takeaway is, I'm not interested in your variational principle, Tushar, fine. Go home and study this function. Prove something non-trivial about this function. You will have some interesting mathematics in your hand.
Excuse me, can I ask a question?
Yes.
So if you want to prove this take this variational principle and prove something for arbitrary homogeneous space, do we have something equivalent, like equivalent definition, for example, for heuristical subgroup? Because you are taking A as a matrix, but now suppose you want to do something similar to heuristical subgroup and you take
yes,
heuristical leaves. So do we have, can we make something similar?
I certainly, that's exactly, you're asking a question in the same theme as I was just saying. We haven't done it. Our paper is just the tip of the iceberg. It's just the most simple situation. It's the variation principle. I mean, one way we thought of it is we wanted to sort of unify a bunch of results from before. It turned out by luck that we could get some new results as well, which I'll also mention. But you're absolutely right. Extending all of this into the land of more general homogeneous dynamics is waiting to be done. And I'm going to, so the next coming up, what is a template? So we need to understand, what can templates say to answer your question, Shahryar, about this more general situation where A is not just a matrix.
Thank you.
Yeah, where we're not just looking at this very special UA, right? You want a more general subgroup, absolutely. Okay, so just to, this is me repeating myself, but this is the real question. Given a matrix, or as Shariar says, given a horospherical subgroup, then how do you study the analog of the successive minima functions? They're out there. So our answer was this idea called a template. So I'm going to motivate it by saying, when can a given function from 0 infinity to RD be approximated to within an additive constant by the successive minima function of some m by n matrix? And our answer is that it can, if it can be approximated by what we call an m by n template. So here is a definition by picture. So this is an example of a 1/2 template. Okay, so this is what it looks like. This is a template. Unlike the successive minima functions, HA, which are extremely difficult to draw. For those of you interested in the geometry of numbers,
you muted yourself, I believe.
Tushar. Hello? You're muted, Tushar.
No, I don't think so. Or at least one of them is not muted. No, I can't hear either.
Tushar, can you hear us?
Yeah, looks like.
And I don't think
he maybe he was trying to join from another device, and now we seem to.
And I'm not sure you can see us either.
No. Yeah, now it says that it's indeed muted.
Sorry, well, was everything? I got a message about muting.
You're back.
Is it good? Can you hear me?
Now we can, yes. Okay. So tell us about templates before we're out of time.
Oh, sorry. So this. No, but 1 second. Something is wrong, because you can't see my definition of a template, right?
We have a picture. We can see a picture.
No. Yeah, so there's something went wrong. So yeah, we're not supposed to be seeing the picture. You should be.
So can you move to another slide?
No, I mean I can, but
we cannot.
You can't. So it seems that my screen has crashed.
Can you stop sharing and then start again?
Yeah. Sorry.
Yeah, I apologize for technical difficulties during our flight.
So
we expect some turbulence.
Just when I was telling the definition of templates, which is great. Okay, so let's see. Sorry. Internet audio. Back to.
Yes, it's the same picture now. But yeah,
now, okay.
Now it's moving. Okay, great.
Sorry. Okay, let's. So if you keep that picture in mind, the first two parts of a template are that the Fi, okay, so the coordinates of this map F, or the components, F1 is less than equal to F2 is all the way up to Fd, and the slopes, remember these are piecewise linear, these slopes are between -1/n and 1/m. Okay, now comes the non-trivial part of the definition of a template. So for every j and every interval I such that you have a strict inequality like this, so fj is strictly less than fj plus 1, you look at this function capital F of j, where you sum all the fi's up to the jth. Okay. So the two things we want for this capital Fj is that it's convex. So we call this the convexity condition. And the next thing we say is that this capital Fj should have slopes in this set. And so this is something we like calling the, so this is convexity of this function. And this one is what we call the quantized slope condition. So its slope is in this finite set. And if you look at this definition a little and play with it, what you're going to get is that each of the FIs can take on at most finitely many slopes. Okay, the little FIs. Okay, so just because of time, I'm going to skip through some things now. So the big theorem that answers our question in this very basic case is that for every matrix A, you can find a template so that the successive minima and this template are up to a bounded additive error of one another. And similarly, for every template, you can find a matrix such that this happens. Okay. And the special case in the case of m equals 1 was due to Roy, Damien Roy, and that was actually extending and completing in some sense the program started by Schmidt and Leo Summerer. Okay, so that theorem actually can be quantified via something, it's a corollary of this variational principle. So this theorem says that if you take any class of functions closed under finite perturbations and you define some set, right, some set of Diophantine interest, so you look at all matrices whose, say, successive minima functionals are in your class S, then you can get the Hausdorff and packing dimensions via these two formulas. So you're taking a SOAP over what we call the lower and upper average contractivities. And what is the upper or lower average contractivity of a template? Okay, so for time, I'm just going to jump to the picture. And what it's doing is it's sort of counting the number of, if you imagine these as particles moving, and this is time, it's counting at each stage the number of pairs moving towards each other. Okay, so in our paper, you'll see that we describe some strange laws of the physics of this world. But my point is that to compute these is just basic combinatorics, right? You're dealing with the combinatorics of piecewise linear functions that are extremely nice, like the slopes belong to a finite set. So can't be better than that. So now let's say we want to compute the Hausdorff dimension of the singular matrices. So you choose this class, SingMn, and you define S to be the set of all functions that satisfy this condition. Now this class S is closed under finite perturbations, and so our variational principle applies. Okay, so my slides have a sketch of the proof, but maybe because of time, I should end with some problems. Okay, so should I can I have maybe maybe 2 or 3 minutes, or should I stop now? I could stop now as well.
Yeah, I don't know. Maybe you can stop just to have a round of applause, and then people may ask questions. And of course, first question would be, what are the problems?
Yeah.
But anyway, up to this point, I enjoyed the talk a lot. So thank you very much.
Let's, sorry for
just in case some people would like to leave sooner than 5 minutes. Let's thank you, and then please tell us about what you want.
I can say something a bit about problems. Yeah, and I just noticed in the chat. I'm sorry for making that error, but I'm very glad that you corrected me, Dima.
No, that's
so fine. Apparently, Shirali was a student of Manfred Einsiedler and Nimish Shah. So, in the family, in the broad sense, maybe not grandfather.
Yeah, we're all relatives here.
That's right. Okay, so let me end last 5 minutes. Let me just pose some questions. Now, this is very broad. As I said, there's lots of questions to be asked here. So one of the things you could look at is, just like you have the very well approximable numbers, you could consider the very singular numbers, right? So these are those matrices for whom this limit is minus h1 of t over t is positive. And you could look at level sets and say, hey, what about the Hausdorff dimension of all matrices whose uniform exponent of irrationality is equal to some number, let's say omega, some parameter omega. And though we can prove certain asymptotic formulas for both the cases when omega is small and omega is large, it is very rare that we can actually get formulas. So here's a formula that I'm particularly happy with, is that in the case of 1, 2, and actually we can do it for 2, 1 as well, but in this case, we actually have precise formulas for the Hausdorff and packing dimensions of these level sets. And this is what they look like. So the one problem that I think is really, really interesting, but it's not an easy problem. So maybe, I don't know whether I would call it a PhD level problem, is to find formulas that go beyond our case here for the setting of 1, 2. So I just want to point out that even in the next case up, so when m plus n is equal to 4, we don't even have conjectural formulas for the dimension in these cases. Okay, so that's waiting to be resolved by the brilliant participants of this seminar. In fact, if you can't find formulas, it would be really interesting to know when these functions are continuous. If they're continuous, I have follow-up questions for you. So once you can determine this problem, please write to me. We were very optimistic about this problem about 5 years ago when we started this research in 2016. But eventually we realized that things could be quite tricky about this problem. So I've written some of the dangers on this slide. Another question that I think is very interesting is, what about a double level set? So a level set where you fix both the uniform and the standard exponents of irrationality. I'm going to skip this quantitative Schmidt conjecture. I want to advertise a very beautiful result where, instead of taking this very, very nice GTUA, what if you took some other diagonal flow And is it possible to compute Hausdorff and packing dimensions for the divergent trajectories under such a situation? Okay, this is sort of an intermediate next step in some sense. And again, we're back to low cases, 2 and 1, 1 and 2. So when m is 2 and n is 1, this was recently resolved in a beautiful paper by Lingmin Liao, Ronggang Shi, Omri Solan, and Natalie Tamam. And Natalie and Omri are students of Barak Weiss, who's spoken at this seminar. And Barak mentioned that Omri has some new results about this. So stay tuned for them. I hope Omri will be able to speak about them at this seminar. Since Osama asked a question, here's a question about Sing 2-1, but then intersected with a fractal. So BCC, one of the problems in their paper was, what's the dimension of the set of vectors in Sing 2-1 whose coordinates belong to Cantor's middle third set? And Osama Khalil has a beautiful paper on this, where I think Osama has some very, very good bounds and some ideas on trying to really hit it on the head. But at this stage, I think we just have bounds and a conjecture for what the answer should be. And I'm going to end with, this is a question for Shahryar and Dima. Those of you who know, I think Shahryar spoke about this either at this seminar or the York seminar. If you take instead of singular matrices, you could look at the epsilon Dirichlet improvable matrices. And I would love to know more about the maps, epsilon maps to the Hausdorff dimension or the packing dimension of the set of epsilon Dirichlet improvable matrices. Again, I think there are some bounds due to Shahryar and Dima. But I want to point out, in case you're wondering, we don't even know this answer when m equals n equals 1, as far as I understand. It's not published. In the case of just continued fractions.
Yeah, I think Yuta Cheyong and Nicolas Chevalier, they have a result that is near optimal for m is equal to 1, I think, or n is equal to 1, I don't know, for vectors.
Yes. Yes.
On their Duke paper, 2016 paper, it's like near optimal. It's almost optimal.
Yes, yes. I remember that formula.
Yes.
It's like it's an asymptotic, right?
Yes, it's an asymptotic formula. Right?
Yeah, yeah. But
it's only for vectors, yeah, but not for matrices. Yeah.
Only for vectors, not for matrices. But as yet, there's no equality for m equals n equals 1. I mean, no asymptotic, right? Like on the nose. It's very tough. And if you want some flavor for, this one-dimensional problem about not matrices, but numbers, m equals n equals 1, I recommend, if you want to see how complicated this question really is, in the 1D case, I strongly recommend Carlo Carminati and Giulio Tiozzo's paper, Bifurcation Locus for Numbers of Bounded Type, and Gugu Moreira's paper on the geometric properties of Markov and Lagrange spectra. I hope these authors will eventually be invited to speak at this seminar. These are very amazing papers. Both of them are very beautiful. Okay, so this is where I'll end. This slide is even more questions where I'm hoping that you will tell me about how templates are being applied to a problem that in dynamics and number theory that, means a lot to you. Okay, so I'll stop here. I'm sorry for going on for very long.
Okay, well, let's thank Tushar again. Probably we should invite him for a series of talks. Maybe at some point it will be achieved. Anyway, we are out of time, but that's the beauty of having an online seminar, so people can just leave. And if anybody has any questions, we can stay for a while, regardless.
And yeah, I forgot to mention that the paper is very long. And, so just know that it's tech support. So if you have any questions, just write me an email and I'll be happy to respond about any questions you have about the paper or the project. I know it's 120, 30-page paper. So I'm happy to provide tech support. So just.
So can I ask a general question?
Yeah.
So you okay, so you have this notion of templates, which generalizes what was done by Damien Roy and others in particular. So Damien doesn't use the word template. He uses something like end systems, rigid systems. I don't remember exactly the terminology.
Yes.
So in principle, what are the principal differences? Yeah, and Demi, I see your hand. So let's.
So this is a really excellent question. So.
So I just heard Damien talk about it 2 days ago. So I'm trying to compare.
The short answer is that templates generalize the rigid systems of Roy, and the rigid systems of Roy generalize what are called N-gamma systems of Schmidt and Samara. Okay, so now, when we wrote the paper, we didn't look at Schmidt, Samara, and Roy. In fact, when we proved these theorems, it was at Ames Square. We were in San Jose, and we were just writing stuff up on our notes, like whiteboard and paper. We didn't really look at their papers at all. And so when we finished the paper and we sent it to Damien Roy, because then we heard from other authors that, oh, you should, send this to Roy. This is long before all this was, initially it was just had the result about Hausdorff dimension of singular, right? Which is something that Schmidt, Samara, and Roy don't actually mention at all. And so when we sent it to them, Damien did a beautiful service to us, and he sent us a long email translating between his notation and our notation. And this email pretty much with a little bit of epsilon addition is the appendix of our paper. So there's a one-page translation. If you are reading either Roy's 2015 paper, or if you're reading Schmidt Samara 2013 or 2009, the appendix tells you how the terms are related. But templates are a definition which I think are not contained in any of those three papers. Otherwise, Damien would have said something to us, I think. So I'm sorry for a vague answer, Bhima, but this is what I've got.
But in all these cases, it is some function which approximates the successive minima functions of the project.
Exactly. And I think this idea is really due to Schmidt. The seed of this idea is due to Schmidt, and our paper is sort of dedicated to him because of this. Because this heart of this idea is brilliant.
But in the case, so I understand that Damien only wrote about the vector case. So in the vector case, is it possible to take his definition and plug it in your technique with the variational principle, or there is some technical abstractions to that? I'm just trying to see what is really different.
No, you can, but our definition is more general. So Damien's rigid systems.
In what sense?
we need to, So we'd need to add one, just a small thing. One thing comes to mind, we would need to add a condition to templates that we call balanced. And so a balanced template is one where the sum of all the coordinates, so little f1 plus little f2 all the way up to little fd is equal to 0. And you might say, well, these seem like a pretty strong condition.
But that's second Minkowski theorem, right?
That's second Minkowski theorem. So it turns out that every template is within a bounded additive error, right? You can translate it and get it to a balanced one.
Mm-hmm.
And so, yeah, the answer to your question is yes, all of the things would work. You just need to change the terms and add a few adjective or two.
Mm-hmm.
So you can't just replace rigid system with template. That answer is no, but there's a dictionary that tells you, which is the appendix of the paper, it tells you what adjectives you might have to add. Maybe you have to say it's an integral balanced gamma template or something like this.
Okay.
I've forgotten the details, so I can't. But really, this is all because of Damien. Okay, so the appendix, we thank him profusely for this because he did the hard work of translating between our notions and his. And his notions, again, you need to translate between his ones and Schmidt's summary. That's also not hard.
Okay, so there's a question from Demi. Alan, Demi, would you like to speak?
Yeah, if there's time, I'd like to ask a question that's a bit tangential.
Yeah. Please,
so,
go
yeah.
ahead, Dani.
Thanks for the nice talk, Tushar. So early on, you had a question which you attributed to Starkov, and I'm just trying to understand. So as far as I recall, all the Dirichlet improvable numbers are badly approximable, and I think there's a conjecture.
No, it's okay.
Is it the other way around?
Numbers, yes, but not in high dimensions.
I think Demi is asking about numbers.
You're asking about...
I'm meaning to ask in higher dimensions. So so it's not true in higher dimensions.
In higher dimensional, singularity implies Dirichlet improbability, and singular guys are not badly approximable.
Okay.
No, it's Starkov's question is really about something with an unbounded orbit, which goes to infinity, but very, very, very slowly. So it's definitely not about badly approximable numbers.
Okay, so I was trying to get my head around why these two things were not contradictory, and I guess if I in my head one of the things was wrong, that probably explains it. Thank you.
Yeah, there is an implication, but it goes other way around. Badly approximable implies Dirichlet improvable.
But Demi, there's a lot of interesting, so one way you can think about the picture, the global picture, is think of VWA. You know the VWAs, right? The VWAs, and then think of singular. Okay, so you've got these two sets. They have a non-empty intersection, and the symmetric difference is also non-empty. Okay, inside them, you've got the very singular, and you've got the Liouville. So the Liouville sitting inside VWA, and the very singular are sitting inside the singular. Now, between the very singular and the Liouville, there is like an onion. There's many classes between them and their supersets, which are the singular and the VWAs. And the punchline I'm getting to is that all these sets are sort of full in their superset containing them. So it's actually very interesting, the landscape.
Yeah, this is kind of where my question was coming from. So I've got confused about which way around the inclusion goes, but I remember I think Barak Weiss saying to me that he thought that the dimension of whichever way around the inclusion is supposed to be, the Hausdorff dimension of the complement should still be full. And I was just trying to put all these things together with this question that you asked.
Yeah. So I agree with Barak. What Barak's idea is absolutely right. This is not in the literature as yet, but this is true. If you're willing to believe me.
Yes. So I think we can prove it in the paper with Shahriar, which is yet to be written, and it's kind of a paper which. Okay, but maybe I can talk about it later at some point.
Emmanuel, did you have a question? Or
yeah, no, I was just wondering about this question of Starkov, because you were you were mentioning the question. Do you know if you can find such an orbit from a algebraic point? So
yeah,
you cook up these orbits, but
yeah.
One, that would be, if you start with an algebraic, so a matrix A with algebraic entries.
I think that's that's an amazing question. I don't have an answer. I want to say
yeah,
let me get back.
I don't know.
Let me get back to you on that. It's interesting. I don't have an immediate answer for you.
Yeah, I was asking myself this question a week ago. So
that's a lovely, it's such a natural question. You're saying if you start at
can you
it's difficult. It's a particular you've picked an orbit, right? So, and you've picked a very special point. I'm just trying to see what could go wrong.
Yeah, because the way you construct those orbits is somehow it's not constructive, right? It's by showing that there are many, but if you want to put your hand on one particular example,
it becomes difficult.
Right.
Yeah, because what we're doing to construct those orbits is basically we paste a bunch of templates together, and these templates, they have to and remember, right, like, so all the templates are going to be within a bounded error of the matrix. But to say that, oh, I always want to be within a bounded error of an algebraic point, this is tricky. I'd have to think more about it. It's a lovely question.
Okay, any other questions? Well, maybe it's time to give the final round of applause to Tushar. It was really a great talk, great historical introduction to the subject. I wish we have more of those.
Maybe we can have a second or third talk of Tushar next semester.
I would be happy to. I mean, maybe I can try and answer.
I don't know what's going to happen next semester. Hopefully something like this online series will continue. We'll have to think about it. It would be a pity to just stop and go back to our classes. So yeah, next semester we'll see what happens. And next week there will be a talk by Asaf about basically some techniques related to asking Margulis Moses stuff and those integral inequalities that Tushar mentioned.
Oh wow!
So please come back. And at that point, let me stop the recording, which I probably should have done a long time ago. And well, wish